Hi there, this question deals with modelling with first order differential equations, so let's take a look at this question. Question number 1. A bacteria culture starts with 500 bacteria and grows at a rate proportional to its size. After 3 hours there are 8,000 bacteria and we need to find the number of bacteria after 4 hours. So first of all, let me denote capital B. So let me let capital B be the amount of bacteria and using capital B, let's create a first order differential equation. So it says that the rate is proportional to its size. So whenever we see the word rate generally means d by dt, so it's a rate with respect to time. So in this case it's dB over dt, and that is proportional to, so let's use the mathematical symbol for proportional to, so that's proportional to the size, and this size relates to the amount of bacteria, so in this case it's proportional to B. Okay, and let's get rid of this proportionality sign. Okay, so to get rid of the proportionality sign, so in my next step, dB over dt, and that is equal to kb, and k in this case is our constant of proportionality. So let me just say that k is equal to a constant of proportionality, or a proportionality constant. Whoops, so let me make it as clear as possible. So k is a proportionality constant. So this is a first order differential equation. So to solve first order differential equations we need to use the method of separating the variables. So I'm going to bring my dB and B terms to the left. So in particular, if I take this B term to the left, I'll have 1 over capital B dB. So I brought my capital B and D capital B terms to the left hand side, and let me keep the K and bring the dt term to the right hand side. So I've separated the variables. So after separating the variables, let's integrate both sides. So let's integrate. So let me write that down. Whoops. So let me be as neat as I can. So let's integrate both sides. So that meaning, so let's integrate the left hand side. So 1 over capital B with respect to capital B. And let's also integrate the right hand side, so let's integrate k with respect to small t. So if we integrate 1 over capital B, so that should give us ln capital B. So that is what we have on the left hand side. If we integrate k with respect to t, we're going to get kt, but don't forget we need to add c. So c here is our integration constant, and we need to add a constant, in particular if we have an indefinite integral, which we have over here. So c is a integration, so c is our integration constant. So let's have a little note of that here. And at this very stage, so ln capital B equals kt plus c. So let me rearrange for capital B. So capital B then would be e to the power kt plus c. And if I go one more stage, I can divide this exponential term using a rule of indices. So e to the kt plus c, using the multiplication rule of indices, that is the same as e to the kt times e to the c. So remember the multiplication rule of indices, whenever you multiply two terms having the same base, we add the powers. So in the sense I went backwards in this stage. Now e to the power c, so if I take a different coloured pen, so let me take this red pen. So e to the power c is a constant. So I'm going to replace e to the c by another constant. So I'm going to choose the letter capital D. So if I let capital D be e to the c, I can rewrite this equation here as capital B, and that is equal to e to the c, which is capital D, a constant. So it's going to be capital D, whoops, here we go, nice and clear, capital D e to the kt. So this is what we have for the moment, but let's go back to this question. So it does say, if we reread the question, a bacteria culture starts with, so the word starts means at the time t equals 0. So it starts with 500, it says bacteria. So when t equals 0, capital B, the amount of bacteria, is 500. So that is the data presented to us according to the question. So let's use these values for this equation over here. So t equals 0, b equals 500. Here we go, if my memory serves me rightly. So in this case, so when t equals 0, capital B, so that being 500. So if I replace in this equation that we have, so we're going to have B, which is 500. So 500 is equal to capital D, e to the power k into, and t is 0. And e to the power 0, so this term, e to the power 0 is 1. So our value of D is going to be 500. So that is the value of capital D. Let's plug that into this previous equation to see what we have. So if I plug D equaling 500 into this equation over here, so we're going to end up with capital B, that being 500 e to the power kt. And let's go back to the question. So it also says that after 3 hours there are 8,000 bacteria. So in this case, when t is 3, so let me make a note of that over here, the amount of bacteria is 8,000. So in this case, B is 8,000. So let's use this data. So let's use this data and apply it to this equation. So when t is equal to 3, the amount of bacteria, capital B, is 8,000. So if we apply this data to this equation that we have, so we have B, which is 8,000, that is equal to 500 e to the power k, and t, which is 3. Now I can cancel these two zeros with the same number of zeros on the left hand side. Okay, I can also cancel the 5 with the 80. So 80 divided by 5 is 16. So our equation would be e to the 3k as a result of the simplification. That is equal to 16 on the right. Okay, and if I take natural logs on both sides, we're going to have ln e to the 3k, which is equal to ln 16. If I use the power rule of logarithms, so I can bring this power to the front to give me 3k ln e, which is ln 16. Now ln e, as far as this term is concerned, ln e is 1 when calculated. So we're going to have 3k, and that is equal to 16, ln 16 rather. So k, when I rearrange, is 1 over 3 ln 16. So that is the value of k. Now with that value of k, let me replace into this equation here. So if I take a different coloured pen, maybe this purple. So if I plug k into this equation here that we have here, so let's see what we're going to have as a result. So if I go back to blue, so as a result we're going to have b is equal to 500 e to the power. Now k we found, so I'm going to copy that down, 1 over 3 ln 16. Let me put that term in the brackets, multiplied by t. So this is what we have at the moment. And we haven't completed the question, so let's revisit the question. So they want us to find the number of bacteria after 4 hours. So using the equation that we have up to now, we can certainly find the number of bacteria after 4 hours simply by replacing t by 4. So let's do that. So let's replace t by 4 in this equation that we have. So when t is equal to 4, so, and I have some space over here, so let me use this space here. So capital B is equal to 500 e to the power. So we have a 1 over 3, so it's 1 over 3 ln 16, so ln 16 multiplied by 4, so remember t is 4, and let's calculate this. So this is where our calculators kick in. So we should have something like 20158 point, so 20158.74, but let me round this. So let me round this to 3 significant figures. So let's say 20200. So 20200. So it's 20200 to 3SF. So there we go. So that is how the calculation is done. So in this case, this is an example of modelling with first order differential equations in relation to question 1 that we've completed. So I hope you found this video helpful. I hope you found this video clear. If you did like the video, be sure to subscribe, and I hope to see you again. Thank you.